start, so we can welcome Marc-Oliver Pahl, that's right?
Yes.
And he's from the Technical University of Munich, and he will give an interesting talk.
Yeah, thanks for coming. Thanks for the introduction, Randy. Yeah, I will talk a little bit about taming the Internet of Things, and I will talk about a middleware system that I'm working on together with my team since 2008. And this is the northern light from the mountain here just 2 days ago. We were quite lucky to see it. Okay, good. Little background, so I studied not in Munich but in Tübingen, which is also in the south of Munich, and I studied computer graphics and media science there. And then afterwards I changed to computer networks and distributed systems, and also did my PhD in Munich. And currently I'm leading a team there with 4 PhD students, and we typically have about 20 master students to do their final year projects, like their bachelor and master thesis with us. And I'm currently doing habilitation there, which is in Germany the formal qualification for becoming professor, even though it's not mandatory in computer science because often people also don't have it. Yeah, I'm doing that, and I'm also involved in teaching, so we have some collaboration in a German-French academy, and so there I'm also directing the digital teaching activities. Okay, Munich is here. So yeah, and it's famous, as you probably know, for the Oktoberfest. And so this is actually at the Oktoberfest, so people dancing on benches, and you have such huge tents. And to actually be allowed to take part in the Oktoberfest, a beer brand has to brew within the city limits. And so this is why we have these 6 breweries still within the city limits of Munich, and you can smell the malt at night. And Technical University of Munich is the only technical university in Germany where you can also study brewery science, and this is the beer from there. It's called Weihenstephan, and you can get it cheaper if you're a university employee. Yeah. Okay.
Good reasons for UIT to also have this.
Oh yes, we definitely want cooperation, yes. We actually do it already, so yeah.
And
Not brewery, no.
so here's some pictures. So if you ever go to Tübingen, there's a famous boat race, and you can also go with these boats a little bit like in Venice. This is actually the computer science department. So in Germany, you have to spend 3% of the budget of each public building for art. And computer science did a very good investment. They put these large slides here, and so they're parabolic, and it's like a free fall when you go into them. And yeah, this is my core team, so these are the 3 team members, so Lars, Stefan, and Christian, and me. And this is actually in France last year. Okay, good. Now coming to a little bit more technical stuff. So we basically have 2 research lines. So the first one has to do with secure and autonomous management of Internet of Things systems. And then we have quite some projects in the past and also some running. And the second one is also digital teaching, and so I introduced in 2004 already the biggest computer network lab course in Germany, where we had more than 2,000 students so far, and these are multiple courses, and so they're also on the next page. So these are 3 courses at the moment, and there we're basically teaching how the internet works and some selected topics about it, and there will also be a massive open online course that will start in May, where people can also learn that. Okay, this just is a short background for the teaching. The major research project that we're currently running is this one. It's called DCEN, Decentralized Cross-Commodity Energy Management. And the center of that one is that when you have neighborhoods where buildings are standing, they can produce and consume energy. And here we're looking at how can we decentrally make these buildings collaborate so that we can measure what they consume and what they produce. And we look at, okay, how can we use distributed ledger technology and also AI-based energy production and consummation forecasts in order to optimize the load profiles within these neighborhoods, to also reduce the peaks. So if you're in energy, this is a big thing for the power grid, and also exchanging heat between the buildings. And so this is a project that we're currently looking at. And this is also where I was in Finland last week, because there we had the consortium meeting with some nice people. Okay, so that much to the background, and so now to the main part of the talk. So it's structured that way here. So I will tell you a little bit about what is my goal with the research, then which is the methodology, Then I will go to the middleware that we are working on. I will tell you something about the data-centric interfaces, about the inter-service coupling and the semantic modeling, about security. I will show you briefly how to program it, and I will go to metrics, so how the system performs. Running. Okay, good. Okay, so what is my goal? So my goal basically is, with my research, when you look today at smartphones, then and think back before 2008, we had feature phones and no one was developing applications for that because it was just complex. You could not run them there. And when you look at your phone today, they are multi-purpose systems, so they are actually the computers that you're carrying around. And the introduction of this app economy, so the system that people were able to develop apps and you can just run them there, was giving the entire mobile computing world actually a big boost. Because from that point in time, people were really using this. And for the IoT domain, or the pervasive computing domain, which is this controlling the ambience, this boost did not happen yet. And I say, okay, we have the hardware, so this is a good situation today, but we don't have the ecosystem for the software. Because people can just not simply develop applications for that. It's really complicated because you have all these silos, heterogeneity, and so on. And so this is what I'm working on. Okay, how can we create a middleware that enables us to program these smart spaces in a simple way? So that ideally something collaborative, crowdsourced development like in the app economy here can happen in the future. And so this is the focus there. Okay. Why is it not as simple as for the smartphone? Well, the major difference is because they're actually similar, because for the smartphone and the smart house here, or the smart space, you have sensors and actuators. So for your phone, you have it as well. You have a light sensor, a camera, you have a vibration, you have audio, whatever. So you have some sensors and actuators. But, and here you have it as well, I mean, you can control lights, the shutters, and so on. The difference is, here everything is within this containment, within this shell here, and it's getting controlled by the vendors that provide these devices, and they can implement the drivers. While here, you can bring in whatever you want from whatever vendor, so you have much more heterogeneity. It's not a controlled environment in that sense, and it's also distributed, and that makes it complicated. And this is also why here you can have an operating system that is providing this middle layer with the abstraction, and here you need a middleware, because it's just a distributed system. Okay, good. So what is the methodology? So the methodology is the following. So first of all, where is the research happening that we're doing? So it's at the intersection of different areas of computing, and coming from the hardware side, what we have is cyber-physical systems, meaning that we have systems that are interfacing our environment and controlled by software. Then, and this is interesting because it means that for the first time we can use programs to program our environment. And so this is always where I like to tell the thing, it's like doing magic. Because when you write a computer program, it's like you have a spell, and then when you run it, it's like you execute your spell. And it's happening in the physical environment. And this is a very nice analogy that is also driving me, because I really like to be able to put spells on the environment. But of course it also has another side, because when you're able to do that, you also have the responsibility. Because when you give the technology, people can also misuse it. So think about, they survey you, or, I mean, this is a major threat. Or they even do something with you, because when you think about industrial robots here and someone controls a robot arm in a factory, they can even kill you. And so this is of course large consequences that we as computer scientists developing something for such systems also have to have in mind always, so that we do ethical developments. But I'll come to that a little later. So we have the devices, then we have Internet of Things, so the technology that uses internet technologies in order to connect these distributed devices. So this is the connectivity here. Then we have pervasive computing, so having the computing in everything here, and ambient computing, which is more to the software side. So we have ambient services running in the ambience, and they're controlling what is happening within the ship, for instance. And so we're in the intersection here because we're working on the operating system or middleware that enables such applications here using the technology from here. Okay. Good. More concrete, we have two relevant research lines here. Namely, first, this operating system that is called virtual state layer, where I will tell you something more about today, and also IoT service management. That then, once you have this operating system, it's logical to take the next step and go also to the service management that we have here. I'll also briefly talk about that. Interesting topics. As said, security is very important for the reasons that it's ambient, so we can really affect the humans in the surrounding. Dependability, also important because we are pushing control from the physical level towards the software. So the software has to be reliable, because otherwise, when the light system is only working 30% of the time when you press the button, then you're not happy about it. Or much worse, when your power plant is controlled by software and the software is not running, then this is of course a much bigger impact than this other convenience feature. Scalability, because as I said, when you bring in more devices, systems should still run within certain latency boundaries. And also when it comes to end user usability, but also to developer usability, it has to be easy to program. Also affecting all the rest here, because if it's easy to program, meaning little lines of code and understandable code, then the services will also be more secure, because people can validate what they do and they can also express what they want to do. We do this, and of course also look at the application domain. So user interfaces, orchestration services, other microservices, device adaptation, and then the devices here. So to evaluate that and to increase the development there, we of course also implement some use cases here. The approach, as you see it already, is a microservice approach. That means with this system here, you have small pieces of software that implement something like, okay, there's one service that can interface the controller for this lamp, for instance, another one that is controlling what happens with the switch. And then these orchestration services are dynamically federating the other services to do something. Because also today, when you buy an automation system, everything is often hardwired in software. So hardwired in software, meaning that certain components are connected within the software logic, and you cannot use the lamp from 10 services in parallel, for instance. And so there the microservice approach has an advantage because it allows you to late couple to these services so that you can time share the lamp control here, in essence. Okay, good. And so the four students here, they are also separated like that. So Stefan is working more on this operating system side with caching data there. Jan is working more towards the service management. And then Christian is looking at, okay, how can we apply machine learning in both directions here? And Lars is looking at security. So how can we bring security in? And they're all closely collaborating. I just put now these terms because this is how they are distinguished there. All right, so now let's get into medias res. So when you look at Internet of Things today, it looks like this. So you have, or it often looks like that. You have devices, and then you have some drivers, and then you have some services that you want to do with them. So you want to program, for instance, when you press on the light switch, then something is happening, and so the software of this control service is hardwired to some of the other services there. And what we do is we introduce a layer in the middle here that is decoupling the two. And this is the virtual state layer, because in essence what we do is we say, okay, we have the hardware here, and we have some software here, and in this green layer here, so in our middleware, we represent the digital twins of the relevant functionality of these software components. Because this is also an interesting insight. So software components on the top here, they are the ones managing stuff, and they are the ones interfacing the hardware, but this separation is only artificial. It's only because there is this typical layered model when you look at middleware for pervasive computing that is like that, but in the end, it's supporting software that does something, that either interfaces something here or that doesn't, because it does reasoning here, so taking information that was already there and improving it, or it does some control tasks. Here, you do not only have hardware, but you can also have software. So when you think about going towards an internet weather service, for instance, that could be interesting, or whatever you can imagine. So it's not only hardware that you can control here, but it's also software. Okay. What we do here is we have these digital twins, and what we will also see later in the talk, but I tell it to you already right now, is these services here, they interact only over data. That means this service publishes some data here, and if some other service wants to talk to this service, it has to discover the data and it will talk to the data. And this will invoke then maybe something in the service, and effectively this shifts the interfaces of the services from the normal function-driven design towards the data-driven design here. That means the signature of these services here is always the same. So they have simple access functions, so they have just getters and setters, publish, subscribe, and then something that we call virtual nodes, where you can directly create some socket connections between them, which is actually quite interesting. And the real functionality shifts then towards the data. And therefore it's important how the data is structured, of course. And this is why we introduced this central model repository here, which is a directory of data layouts. So the data is structured hierarchically, and these data layouts are then used here. And if you as a service developer want to know what could be available within one instance of such a smart space, you can look it up here. And then at runtime, you can discover certain data here. And as you already know how it's layouted, because this is fixed already at design time, then you can interact with these data points here. And so this is in a nutshell how it works. And what you can do then very easily is you can create such mashups of microservices where you, for instance, say, okay, you get some data from this router here and it's in a certain format, but you need it in another format, and then you could do something like a filter graph here that is then changing the data, so changing the format of the data here, maybe even deriving some information. And if you have very good services, then you can use the data of this router here to say later if the user is happy or not, which would be a nice service, of course, if you can predict that. Okay, good. And then, of course, you also have the users here, so the end users, and so they are also interfaced through some interface services that are given here. All right, good. And this is then one host here. So we see it as a distributed system, and on each node that is powerful enough, we have then such a component that is managing the data of these other services that are running on this node. So you can also imagine this here as a distributed graph or a distributed database that represents the graph of the entire data that is within this site here. Okay, and this green thing here, it somehow has to organize. And so what we do there is we do a peer-to-peer system that is self-managing. So these components here are then software agents that are finding each other and then spanning this green layer, which allows then each of the services to transparently access all the data that is available within the entire system, which is quite nice to program, as we'll also see later at the end of the talk. Okay. Yeah, by the way, if you have questions at any point in time, just interrupt me, then I can tell you more there, or at the end, of course. Okay, so now keeping this picture and the colors in mind, you can look at it once again. So we have then this central component of the middleware that we call knowledge agent, and this one is managing this data that belongs to the services. And then we have the different services here. They can subscribe, notify, so publish, subscribe pattern. They can get and set, and they can do this virtual node thing that in the end results in a socket coupling between two of the services here. Yes. And here we have those interfacing some sensors and actuators. And looking once again at this layered model, in the middle we have the data, and the data in pervasive computing is typically called context, which I define as all the information that a software service needs as input or wants to put as output. So it's basically all data that is in there. And around that we have the services, and around that we have the interface devices. So of course here we also have devices, because the user interface, we are not brainwired yet to computers, so that we have some of these smartphones, for instance, and around that we have the physical world. And what's interesting about this picture is when you look at typical analysis for middleware from 2014 and earlier, then it typically has these layers. And when you analyze them from a developer or from a design perspective, you can actually connect them here, and then you end up with only having like 3 layers and then this context management. So you can also unfold this. So you would typically unfold it like that. And then this would be the base, and then on top you would have the services, and on top you would have the devices, and then you would have the physical world. Okay, good. So switching once again the view a little bit, colors still stay the same. So from the technical implementation, as briefly said before already, we have then these compute nodes, and for these compute nodes, we do not imagine that we will have computers standing all around. But what I rather think is that, as we've seen it with the smartphones, the processors of all these things will get more and more powerful in the near future. And here you have whatever, a quad core right now, I guess. And so it's easily imaginable that in some years, even the light switch will have a quad core that has enough power to also run services, just because of economical reasons. It will just be cheaper to have one single chip that is using almost no energy than having downsized chips. So we also see it in computers already. And so then we have some of these more powerful nodes. If you have a less powerful node, you can also interface this here because it's just a normal socket connection here. And then we have the overlay on top that gives us logical connectivity. The interesting thing is then that within this network here, everything is just always one hop because the overlay is managing the underlying communication path here. So what we use here at the moment is HTTP2 over TLS, TCP, IP, but as the services are only interfacing with the interface of this one here, we are agnostic of what we use below. So we could also use another transport, could even use information-centric networking as layer here, because the primitives that we offer upwards are actually very close to the information-centric networking principle here, if you're familiar with that. Then we have the services. Interesting here is the services always only connect to their local instance, which does not have to be on the same machine, but they have a one-to-one connection here, which is also very interesting from a security perspective, as we'll also see later. Because that means all the communication goes through our control layer, plus even stronger, because when the data is managed by us, we also can manage all the data accesses. And this is quite advantageous for the security properties. Okay, good. Making the picture even more complete, but don't get shocked. So these are now actual components that we have in there in this software component. So we have a transport manager, connections are managed between the nodes, overlay manager. So this is for maintaining this peer-to-peer overlay. Then we have the request router that is managing what happens with our messages. And then we have access control to the data, and we have the actual data, and we also have some cache logic to improve the resilience and also the access speed to the data that is in there. Okay, good. So this is the most complex architecture picture that I have for the base architecture today. Okay, so now you roughly know how this system is designed. Let's switch to the data-centric interfaces. So this is the picture again that you know already, and there's one very nice thing that you can do when using this data-centric interfaces here. Namely, you can separate the logic and the data of services. So what does that mean? So we have something here like an intelligent power plug. It's interfaced by the gateway service. It has some data here, and then here we have the services that are doing something with the data. And what we can do here now is that within these yellow ones, we only have the processing logic. And here we have all the state, so this is also why it's called virtual state layer. So all the data, and this is very nice because it means that when you think about service management, for instance, you can just update or shut down this here, and the data will still be available. And this is quite nice because that means if you want to save energy or for whatever reasons this service is going down and not running anymore, the data will still be available. And this is interesting for the IoT because you often also have applications where you want to have historic data. For instance, when you want to optimize a heat curve or something like that, you want to have the historic data, but it could be that the device is not even there anymore or the service is not running anymore. Another thing might be that the connection here does not have to be running on the same machine, but it could also be a low energy connection, for instance, and you just want to save the energy of the sensor here, and so you will put it asleep most of the time, and then the data proxy is still here. That means it can still be accessed, even though this device can be in deep sleep for a much longer time, which is quite advantageous here. Okay, and then here we can do the coupling again, as said before. All right, so we can separate logic and data. Nice property. Next important thing, as said briefly already, is we need an explicit context structure. Okay, and what do we do there? So we just have a hierarchical model here, and it uses object orientation. That means when you define what a light looks like, so how the digital twin of it looks like, you can use this model and extend it to have, for instance, a dimmable light that has just some more properties, but still inherits from the normal light model. And so here we have a humidity and irradiance sensor, and it looks like this, and it inherits from these definitions of the data types that we have there already. And this is quite important because that means when you have a digital twin of a device here, it's not the unique digital twin of this device only, but it contains also other models that were defined before. And when you think back about the interface thing I was talking about, so when services want to discover each other, the important thing is that they want to find the signature of the other service. So they want to find, I want to have a heating control, for instance, and then they would look for signatures here that they know. And when you think about normal interfaces, then you have something called polymorphism, meaning that you can have multiple interfaces at the same time. And that would mean when you look for a light, you will also find dimmable lights, for instance. And that would be quite good in an IoT environment, because when you want to switch off all the electric devices within one room, for instance, you would want to search for something that is control electric devices, and then you would want to find all the devices independent of what their functionality is. The nice thing with this here is when you have this, then you can discover all the data types of the subnodes that you have in here if you provide an appropriate discovery mechanism there. And this is quite interesting because when you have normal interfaces and you inherit from them, you have something called shadowing. So if the method is called open window and you inherit from another interface that also has an open window, then one of them is shadowed, of course. And with this thing here, you can inherit on multiple levels. That's because we have this hierarchical nesting here. And that means when you have, for instance, a controllable power plug here with 10 outlets, you can have 10 times the same model here in the next sublevel. So that means you can have a discovery not only on the root level, like you would have with function signatures normally, but each of these nodes can have the same type here. And then the addressing here is also hierarchical. You could discover each of them separately from each other, which is a very nice property, which is very powerful for implementing these IoT scenarios. Okay, and here I wrote ontology. Sorry for not having translated that. So here it says ontology for smart spaces, because as I told you, so I will also have a slide about ontology later. So this one here is representing these information that the services provide here. And if you have a directory of all the information that can be provided, then it's describing everything that is possible in such a smart space. And so the word for that is also ontology, because it describes everything that you can interact with in there. And this is also another nice side property, because if all people would use this system, for instance, then we would have a description of everything that is possible in this IoT world at the moment, which is also a very nice idea here. Okay, good. Another point here, standardization. When you think about crowdsourced development, so this is what I want to have. So if you buy a power plug, then you want to write a driver for that because you just have the skills to do so, and you provide it and someone else also has another power plug and writes a driver, ideally both would use the same interface, because otherwise the software development will be complex again, because you will have to search for 20 different interfaces for this power plug. And therefore, if you have this directory and the inheritance here, what you can do is you can inherit from other models and extend them, which makes sense. But you also need an incentive to do so, because why should you do so? And the proposal here from this publication is to do some ratings, so like the charts for music, that you say, okay, these are the most popular interfaces that you can use for power plugs. And this is interesting information for developers, because if you develop a service that wants to interface power plugs, if you want to be lazy and not do too much work, you would only choose the one that is most popular, because it would have most spread. So you would be able to interface most of the power plugs if you use the most popular one. So this is the incentive for the developer being the consumer, and for the producer it's the same reason. So as most people will probably use the most wanted or most used power plug interface, then you as a developer should also support it, because then you're compatible with all the cool services that are out there. And so this is why this is also an interesting proposal towards crowdsourcing this standardization aspect. Okay, good. Yeah, certain fixed methods. So as get set, then we have some locking mechanisms, because we need some transactions. So when you want to implement something with security, you don't want the door to open, for instance, until you really check that the person has the identity it gives. We have to have some certificate-based security. We have these virtual nodes that are about the synchronous communication. And so this is basically the interface. So it doesn't have more methods. So you just have these methods, and as you can imagine, it's quite simple to understand them and to use them. And the complexity is then only in these models, and you've also seen that it seems not too complex to program them. Okay, good. So now to the coupling. So the coupling is of course important, because the coupling of services limits what you can implement. Because for some services you need synchronous coupling, for some you need asynchronous coupling, you need delay tolerance and so on. And therefore this system has the two coupling methods I was talking about. So let's imagine we have such a knowledge agent in the middle. The service 2 is providing some data. Service 1 gets to know about it, and then the service wants to access it. And so there's the simple hierarchical access pattern here. You just go to the service 2, and then you get some data node that you want to have. And for regular nodes, you just have the access to this thing. And what is interesting, that it doesn't go into the service. So the service is not bothered at all here. Service has the data here, and so here all access control and so on is happening, and then you get the data. Okay. For the virtual context, the interface from the consumer side is the same. So you still do a get, but these virtual nodes register, so their service registers a callback, and then this callback is called exactly when you access the data here. So it's exactly the same mechanism like when you access a dynamically generated website. So you access a normal URL, for you it doesn't look suspicious, but in the background the data is just generated on access. Okay, and this is very powerful, because this allows you to really have synchronous access, which you also have here when you have the subscriptions, because if the notification is fast enough, then the other one can just get the data. But the good thing here is that when you have this, you can also use stream communication, because you can send more data than you would with these distinct database items that you would store there. Okay, and last info here. So this virtual standard, I call it micro-middleware, similar to microkernels by operating systems, because what we try to do there is to strip off all functionality that is not needed, to exactly not run yet another middleware for pervasive computing that is best for entertainment, for instance, but saying, okay, we have only the core functionality, and if you want specific functionality, you can plug it in at runtime. Okay, and how do you do that? Well, the basic thing to do is using this late coupling, so discovering the functionality that we need, and then interfacing it at need. And so this coupling then, as I told you before, happens via the type search. So you have the type light control, for instance. You search for an instance of this data, and then you get it back. And in this case, this is just such a virtual node here. And so then you access this data, and this is then a callback within this service here. And the nice thing is that with these virtual nodes, as with the URLs as well, you can use it for normal function parameter passing, like you would do for a normal functional interface. So you can give different parameters here to the next service, namely your garden and irradiance, and then the service can interact with it. Okay, good. So, semantic modeling. So I mostly told you everything about it already. So who knows what an ontology is? Okay, so almost everybody. So an ontology is the description of the world. That means that you define, for instance, a stool is something that has 4 legs and a back. And so then in your world, this will be defined as a stool, and then you would have it here. And then if someone else defines a stool like, okay, having 6 rows or 5 rows and being able to move, well, this is a little bit a different concept. And if both want to talk to each other, then this happens via a so-called upper ontology, where they define the least common sense what a stool is, saying, okay, it's something you can sit on, for instance. Okay, so this is on the descriptive side here. And on the conceptual, on the design side here, you have a virtual object that is representing what a stool is in your system. You have this instance then, which is a concrete stool that's instantiated. Here you will have models for a stool, so this one will be instantiated here. And then you have a meta model that you use in order to describe what that is. And we exactly have that here. So we have these context nodes that are the instances. We have the models that describe how the light, for instance, looks like. And we have the meta model that tells us, okay, you can nest nodes and you can give them certain properties. Okay, and yeah, context management happens as said using the methods shown before. Then we have these trees. As the data is representing what you can interact with in the service, each service has then a subtree within one of these knowledge agents, and the data comes from the repository, because you need to be able to look it up in the directory, because otherwise you cannot do the late coupling at runtime. Okay, good. And you can do the type search there. So this is exactly the same picture. So we have different agents running here, and here we have the definitions of these constructs, and they're getting instantiated. And if you search for a W2 here, then you would get the address of the S2 here, for instance, at runtime. Because it instantiates this, it also extends it, so you would also have different functional tags, but you would also find this thing in here. Okay, good. Now, security. So, security is probably the most important topic that I see for this Internet of Things. And why? This is a little bit of a motivating slide. When you think about Facebook, who is collecting the data that is on Facebook? Well, you're doing it and your friends are doing it and they're putting it in there and then it's there. So this is probably most of the data is coming in like that. If I want to write something bad about someone, I can do it, so I can be biased and so on. When I have the sensors of the IoT, then the situation is much worse. So first of all, they are not biased, so they will collect the reality if someone programmed them like that, and they can do much more frequent sampling. So they can tell much more about me than a human would normally do. And this makes the situation much worse regarding the data, because the IoT already has, but they are still siloed. But when you think about connecting all the things in the world and giving access for purposes of implementing something, then it gets much, much worse. Okay, and so there, it's a little like that. So the IoT is a much bigger data cranky than you have for Facebook, for instance, today. And it gets worse, because what do we have? Since a few years, we also have AI, and we have it for longer, of course, but we start using it more heavily for big data analysis, for instance. And the combination of this one and the big data lake or data availability here is, of course, a problem. Because now, before it was like, okay, someone had the data, but they probably didn't have enough people to analyze it. With this one, we can analyze it, and we can profile people and so on. And therefore, we as developers have to take care that people can express their privacy. So what they want to happen with the data. So privacy, I would define as, I know who uses my data and I know what they use it for. And so this is what I want to define. Okay, and so this slide is, let's not be silent, let's act. So as developers, we have to implement the mechanisms. Because if we do not have them in the core of the systems that we provide there, we cannot retrofit security. If the data is out, it's out. Okay, good. So how do we implement security? So we try to implement security by design, meaning it's non-circumventable. You have it as core part of this abstraction. And as said before, as we have the data, we can do so. Because if someone wants to develop a service for our system, they can implement whatever logic they want, but they will only get the data access that we allow them to give, and not we as system developers, but the actual people who own the data should be able to give these permissions. Okay. So this brings us a little bit into the service management. So the service management is familiar to you because it's exactly the same like you have for the smartphone. You have developers somewhere on the planet, they upload their creations to an app store, and from the app store it's getting deployed on the smartphone or in the smart space. For reasons that are this distributed thing that I said at the beginning, it's not as simple as on the smartphone, but the components are overall the same. So you have some service manager within the space, so it's like when you open your app store on your phone here, and then you have some distribution of the software to the different nodes where it's running, and then you have some management and updates going on there. Okay, so quite straightforward. So the only difference is that you have this site local manager and it has some node local counterparts that are taking care that everything on each node is getting managed. And then in the middle we have this connecting thing, which is the middleware that is running there. Okay, now the same picture, just with a little bit more information. So what do we do there? So let's maybe switch back again. Or let's stay here. So no, let's stay here. So as you remember, we have the separation of the logic and the data was structured as nodes. Okay. So as last security resort, or as first security resort, what we do is each node does not only have this type tag, but it also has access group identifiers for read and write. So you can, like in a file system, you can define which identifiers or which group can read this data and which group can write this data. So this is what we have in here, and so it's at each data node. So you have to define that. And interestingly, you as developer define this already at development time. So at development time, it's clear which groups may access something. So you can imagine saying, for instance, okay, I have a surveillance camera and I have the group camera access, and everybody in the space here who is of group camera access will be able to access the cameras in there. Okay, good. So how do we, and on the other side, the services also need this information. So you do a simple match, so it's a role-based or group-based access control, saying the service has some group memberships here, and each data has some group memberships, and if they match, if you have at least one match, then you can access. So that means the service has some groups that it belongs to, so it belongs to the camera access group, it's getting shipped, it still belongs to the camera access group, and if it accesses some data, it's getting checked if it belongs to the camera access group and the data are accessible in read or write by this group, and if so, then the access is granted on the lowest level. Okay, so if you want to implement that, you have to secure these metadata to which group the service belongs, and therefore we use certificates. So these are normal X509 version 3 certificates. Developer creates one, uploads it here, and then if you are known to public-private key cryptography, you need to know the public keys, and it's not practical to have all the public keys of the developers. Therefore, this store is used as trust anchor for the different sites. So then the software is getting signed here with the store private key. It's getting loaded here, and in the site, it's still not practical if you have multiple stores to know all the stores. Plus, as these nodes are distributed, you somehow need a certification that a service belongs to a certain site. So it was legally introduced into the site. And therefore we introduce a third certificate, which is site locally signed. And this one is used then within here. And then the services are put to the distributed sites as they have the public key of the local site here within their own certificate. They can validate it, and then they can run the services if the certificates match with the certificate of the local space. Okay, clear?
How do the end devices get the server-side local certificate?
Good question. So each of the services in here, also these and the Node Local Service Manager, they have the certificate that is also issued from here, and in the certificate they also have the public key of the local site. So each of them has it, and with the certificate, this is signed with this key, and then you can verify it that it belongs to the actual site.
But how can you do that? I mean, sometime the end node has to get this certificate from somewhere.
Mm-hmm.
And how can you?
So indeed, you have a bootstrapping problem.
Okay.
So at the initial time, when you first put it there, you have to trust it. Yeah. And so there, a solution will be to use a normal. So the normal solution is to use a side channel. So to scan an RFID tag or a QR code or something like that. Yeah, good question. Okay, and what is interesting now here, or two things I want to point out. So first of all, we keep all the certificates, which brings us storage overhead, of course. But the good thing is you can then validate if the store tampered with the data, because if you have the certificate, the public key from the developer, then you can check if it's still okay here. Plus, even if you don't have that key, you can still look at if the fields are correct or not. So this gives some security there. And one thing is getting changed here, namely this one here, the access groups the service belongs to, is just a proposal. So this is the maximum that you can grant this service to get. And here the developer gets presented, like in the iOS or the Android interface, these are the access rights, so the app wants to access cameras and so on, and then you can remove some access rights. And then this is stored in the local certificate and then distributed here. And the special thing that we do in here, that's actually quite interesting because it goes back to the beginning of certificates. We use short lifetime certificates, something that doesn't work on the internet because it's just too large scale and you have a distribution problem. But here, as we're in the local site, we do that, and we use less than 1 day certificates, and that brings the advantage that even when these nodes are disconnected and you do some changes in the access rights, the entire node will become invalid after the time when the certificate is down, given that the time is synchronized, of course. So this is the necessity. But when you have that, you can enforce a distributed change of the metadata and the access rights within certain time limits, which is a very nice property for such a distributed system. And the renewal is fully automated here, so it costs, of course, energy and bandwidth, but it doesn't bother the user at all, because it's all happening in here, which is quite nice property. Yeah, so this is not surprising. So the shorter lifetime your certificates have, the more traffic you have for renewing them, obviously. Okay. Another thing we do for security is we say, okay, we take an IoT service as black box. So this is, for instance, you can use even independent of the middleware. When you buy a power plug, then it's doing something and you don't want it to do something else. And if you cannot access the code because it's not open access, what you can still do is you can monitor it, what it's doing, you can learn it, and then you can firewall it. So you can automatically create a model of what this entity is doing, and then when you're confident that now it's okay what you learned, then you can firewall it and say, okay, when it does something different, inform me or even block it. Okay, and so this is also a powerful approach. Black box assumption, passive traffic monitoring is what we do there. We do behavior model, so this is ongoing activity. And then we do anomaly detection. And then we can do firewalling. And this is such a scenario with which we also demoed. So we had a washing machine and we had a front door controller here. And then this is actually a very nice demo because there was blinking firmware update. And as good computer scientists, we always click yes, immediately. And so we did the firmware update, and then suddenly this one was opening the front door because this was just bad behavior. And when you have the other system running, then you can obviously block it. If you say, okay, before it was behaving normally, then there was a software update and it should still behave like that. Interesting here again. So one thing that we always try to do is having as much autonomous functionality as possible to manage the complexity here. The interesting thing when you have multiple sites is that you can learn within the sites, and as all the services are heavily tagged, so the functionality is provided by these models, you can also relate this. So if you have an instance of a washing machine running and I have one running, we can share the information, what these washing machines are normally doing. we can share it with the other sites, and then we have a bigger trust base in our models. We can also look at not mislearning something, ideally. Yeah, so one interesting result is, for instance, when you have tagged data, then, so this is just IoT data that is sent by some of the services. When you look at it, it looks like very cluttered here, so you don't see much. But when you decompose it into the different functionalities, which we can do because everything is tagged in this system, then you can actually find periodicities. And so this is one of the things we look at. This is a very simple case because we just look at one periodicities, but this is one of the activities that we're currently doing. Okay, good. So I'm almost at the end. So programming hands-on. So the system, once again, then looks like that. You have these agents running, they somehow provide connectivity, you have devices connected by software, you have these data nodes that you want to interface in here, and we are evaluating this system continuously because I'm using it in one of my practical lab courses, and so the students have to work with it each semester, and so this is out of one of the tutorials we give them there. And so this is how you actually use the system. So you have one connector, so there's about 10 lines of code that you create this connector to the green middleware layer. And from that point in time, you can just use the normal operations. So this is Java. And so it's really very easy code. And you could even push it a step further by introducing a domain-specific language for expressing it. But we didn't do so because it's very straightforward here. And when you want to get data, you can just get something at an address, get the value from there, and then you can do something like in the normal Java that you do there. And a very nice thing about this abstraction is that you can write very complex applications with very few lines of code. Plus, with this modularization, you have really tiny modules that you can then compose to more complex applications. This I consider also very important towards having more secure and validatable software. Because if you have reuse and it's open functionality at least, or better, even open source, then people can have a look at it and will hopefully point out problems as you have with normal open source software there. But here, especially with the smaller footprints, yeah, it's even better to do that. Plus something that I also did not start looking at too much, but you can also formally try to validate what those do, because you have really simple function blocks in there. Okay, good. Last point, metrics. So yeah, we looked at, okay, what is the latency of the different mechanisms? So this is one setup here. We have a service, and we have then these green components here that are coupled on different computing nodes here. And so, yeah, I mean, these numbers are as meaningful as your implementation is. So we just have a pilot implementation that is implemented by many different students over the years. So it could be much more efficient, I can assure you that. But at least in the network management community where I typically publish, people are very eager to get numbers. And so, yeah, we looked at the latency that is introduced through this coupling here. And when you read a node via a regular node, which is a node that's inside the database here, then you have quite low latencies because one value is that is typically used, even though it's not from too many studies, but it's from one paper, but people typically refer to it, is that when you press a switch until the light goes on, if it's below 200 milliseconds, it's still perceived responsive by you. So you don't perceive it as being laggy and too slow. And so when you see how much time it takes here for local nodes, so the virtual one is the one that is then doing the callback, it's also not much slower, which is also not surprising because the database access here, or if you create data here, should not be too different. Of course, depends on what the service does for doing it, so it could be slower. Then on the local, we have about like 2 milliseconds, and on the remote, we have about 10 milliseconds, which is not only because of the communication delay, because here we have a very fast connection, but also because of our implementation of the serialization and deserialization here. But still, even if it's 10 milliseconds, you can couple up to 20 services in order to still have some thing interactive, minus the amount of processing time that each service has, of course. But that means that the approach is actually feasible. So you can couple certain services, a certain amount of it, like 5, 6, 7, and still have something that is considered interactive by the user. And so this is a very nice result. What we also, yeah, so this is a scalability thing. So if you have, so here we did 20,000 test measurements, and this is the throughput, so how many requests could we process per second on the local node in this case, and they basically see that the implementation in the state that it is scales quite okay, because we have a peak load here, and then it's keep staying there, and here the requests are finally returning, and so this is why it's getting a little slower down here, and so it looks like it should look like. Okay. What we also did is, so as I run it every semester, yes, sorry.
One question from
Yes.
before. If you scale this so you have more remote accesses, do you think this scales linearly, or is this anything else?
It's a good question. So this as I said before, this is the peer-to-peer overlay, and in the peer-to-peer overlay within your site, you always have one hop between each nodes because you're in the overlay. That means the answer to your question in our system will be, yeah, it scales better than linear, because we don't have to do anything in between. It's like when you have a normal internet router, for instance, so it's the IP packet will be forwarded to more hops if we have the hops in between, so it will continue like that even if you have more IP hops in the middle. But your question was probably more into the direction if you have multiple of these hops here.
Yes.
And where could you have that? So you could have that if you have technology changes in between that are not bridgeable by normal TCP connections. So if you would, so I mean, I don't have an example for that, but is it clear what I mean? So it's like, when you think about the communication, you always go the stack up until you have the IP, obviously, and then it continues. And if you then use non-IP and non-TCP, that means that you have to go up to the application layer and repack it and then send it again. And it could be, if you use some exotic communication technology. Yeah, so what we did is, when we couple more of them, then it scales linearly within the IP network. So the answer basically is it depends heavily on your communication layer. So the components themselves, they can linearly scale up. If you have 10 of them, then it just takes 10 times the serialization and deserialization, which is then probably even a little lower than linear here. And we also did the measurements with more hubs, but in the deployment scenario, it doesn't make too much sense to look at these multiple things, because probably these nodes that have such low performance or low resource communication lines are not powerful enough to run these agents anyways. But yeah, still good question, of course. Yeah, good. Then yeah, we looked at the pilot developers. They had tasks and it took them some time to do something. And so they have to do the entire process from they create their own physical device, because it's part of the course, it's the IoT part of the course. They create their own physical device using an Arduino, develop the communication protocol there, and then they use this middleware here, so they create a gateway service here to their Arduino, create the connex models for that, and create some reasoning service and some orchestration service here. And yeah, so the times that they take, that we measure, is for creating the model, and so they have typically no experience with the system before, because they just don't know it, of course, because it's not very widespread. And they also have little experience with the IoT, so they are not very experienced developers, but they know Java typically. And so to create such context models from scratch took them between 1 and 2 hours, the gateway service between 2 and 3 hours, and the orchestration service between 1 and 3 hours. And so overall, it was between 4 and 8 hours to create such a scenario. And so why is the number interesting? So the only middleware that also had the target to do some crowdsourced development and have done some measurements, they described that they did also a similarly complex task to our task, and their experienced developers took about 256 hours for that. And so it seems that this is quite okay to use, the system. And so this is quite very nice result. Also qualitatively, so they said, okay, their pre-knowledge in smart spaces was 5, which is like not much. then creating the adaptation service, so this gateway service. They found it good to do that. The orchestration was even easier because this was the first one, so it was more difficult, of course. And yeah, so this is also nice to qualitatively see that that they understood the abstraction and they could use it quite well. And they have 2 weeks time to work with that, and they get an introductory lecture and then they work with it. Okay, and so this is actually a picture from them. And so this is the device that they create, and we have some nice huge remote control that they can create a game with. And so this is what they do in there. And this is also these lab cores I was talking about at the beginning. Okay, and the last slide is something that I put from my PhD thesis back then. So this is different middleware that was used mainly in the pervasive computing community. And what is interesting here, so sorry again for having it in German, is this here says structured context representation. So you see that many of them have a structured context representation, but what they lack is having a directory for them. So this is also not surprising because these systems here are often created for special purposes. So they are part of a project, and the project is about leisure activities or security in the home, and then they create something that is targeted for this use case. And then, okay, so they also saw, okay, structured context representation is important, but having a repository is not important because their target scenario is not deploying it in multiple spaces often. Okay, then fixed methods to access the context. So that looks a little weaker, but also many of them have it. But what they don't have is this synchronized coupling of the services. So this is something that is missing. Plus, what they also seldomly have is limiting themselves to only providing core functionality. So typically they are customized to do something. So for instance, the context toolkit here, so they are providing functionality for special selections on the data that are there. These selections have to do with the applications that they have in mind. And this is explicitly something that we didn't want to do because we wanted to have something that would be able to bridge between these different use cases that they have. And the dynamically extensibility, this is also something none of these middlewares had, namely that you can plug in functionality. And so one of the master theses that I have currently running, but unluckily the student is not working too fast at it, is also looking at these different middlewares and rebuilding the same functionality using our concept. So saying, okay, they have specialized functionality, we can use it as plugin and then compare the performance between the two. So this is something that's currently ongoing. Okay, so here are some selected publications. There are two things interesting when looking at that. So first of all, most of my publications are in the area of the network operations and management community. The reason for that is when I started some years ago, I was also at the PERCOM, for instance, but back then it was that the pervasive computing and ubiquitous computing communities, they were very much application driven, while the network operation and management, they are not very much into pervasive computing, or not at all actually, so they are more at mobile computing and bigger networks, automatic management, but what they do is they do systematic system management. So they're more into the methodology, what do you need to do efficient management there. And so I try a little bit for many years to push them a little bit more towards Internet of Things and pervasive computing. And yeah, so at the moment with one of the PhD students, we're also trying to target this community again a little bit more. Okay, and so topic-wise, we're going more towards service management and also much more regarding security at the moment. So this is what we're currently doing. Okay, and that was it. Thank you for your attention. So we have 10 more minutes for questions until we have to leave the room.
Yeah, good.
Do you have more questions? Yes, please.
So you presented how your students develop new IoT devices and program them and to integrate that into the system. How about integrating existing IoT devices to use that system? For example, say the off-the-shelf Zigbee or something like that. How can you put that into the system, because you typically don't have any access whatsoever what that light bulb is actually doing.
Yeah, good question. So so let me start answering with, luckily most of them have a smartphone app where you can do something with this. So you have a gateway, and from that point in time they often speak HTTP, so you have a normal REST interface, and so interfacing that one is quite easy. Okay, so you can do that. What you can also do, which is also a very nice approach that I did some works into the direction in the past, but also I'm not having students for that in the moment, is for some of the protocols that you have, you can do again this passive monitoring approach. And if they have a certain structured communication that they have there, you can even automatically try to understand what they do, and can do something that's very interesting. You can, in this system, because you can try to automatically create such a context model, but just listening to what this system is doing, then you can publish it to this central model repository. And then if there's a skilled developer who has free time and wants to do something, this developer can then improve this model by putting more semantics in it and so on. And as long as the tags are kept, it's still compatible to what was auto-generated. And then you can even do some automated integration using some fingerprinting, and then having some generic towards a certain communication protocol interfaces. If you don't do that, what you can also do is you need someone who has skills to reverse engineer what the device does, has to provide it, and the idea is then that this person is putting the driver then or the gateway service to the store, and if someone else wants to have it, can just click and then it's there. So this is the approach to integrate also the existing ones. Yeah?
May I come with a follow-up? Yeah.
Sure.
A lot of IoT devices also actually don't publish. I mean, a lot of devices work in that way that they are pre-programmed to access a cloud service through your internal network, and then your app that you have on your phone actually just talks to the cloud service, and they have no direct communication between each other. So in that case, I mean, then it's really hard to actually access the IoT device in that case, because the only way to actually access is to send data to an external cloud provider, which then takes the communication.
So this is thank you very much for this question, because this is also a very important point, that when you look at today's IoT, most vendors implement exactly the solution you were talking about, namely send data through the cloud. And why do they do that? Because data is the gold. So if you have the data, then you can sell it. Okay, so this is why they want to do that. And this is why I don't want to do that, because I want to govern the data locally. Which is not even the edge, because the edge is still under provider control, but it's really site locally where I want to have this. What you can do there is you can, I mean, we also did that, so you can emulate the cloud. So because you can block it, and then you can emulate enough to intercept the traffic, and then you can use that. And it's actually, from a cost perspective, it's often a good idea, because these cloud connected devices are typically very cheap, because they are cloud connected, and if you manage to intercept the connection and they still believe that they're connected to the right cloud, then you can get the data locally. But indeed, it's not the ideal situation, because this is exactly this model, like your data doesn't belong to you, but to this provider, and you can connect back to this provider. I was also having a project with Philips, and they exactly also have this model. And there it was about connecting some of the Nest devices with the Philips devices and having some security in there, and both are cloud-based. And yeah.
I guess that's then a good thing that most of these IoT things do unsecured communication, so you can easily intercept it.
Yes, yeah. For that it's a good thing. And this security-wise, also this last mile to the device is also something critical, because as I've showed you, so we have control until this adaptation service that is doing something, but if the control afterwards is unsecure, then this is still the attack vector, of course. And therefore, also an interesting research point of view is how can you make it transparent to the data consumer if the data is secure end-to-end, meaning really going to the actual sensor there. And there I also don't have answers yet how you can do that in a usable way. I mean, it's obviously doable, so you can enter whatever text you want to do with this data, but it's a very complex problem because the developer then has to understand the concept of end-to-end trust, and the developer, at least when you think about app developers for smartphones, I'm quite sure that many of these smartphone developers have no clue of what happens inside the smartphone. They're just creating something after having listened to a MOOC, for instance. Yeah. And very good questions. Yes, please.
I was thinking about the digital twins you were talking about. So you're talking about the digital twin for one object. Do you do that for each and every object, or is that just like, do you do it for the whole house, or how do you think about that?
So we do it for every object, and even within the object, we do it for the sub-objects. So the system that we have there is the types that I introduced there have two purposes. So they are first actual data types, so they're like an integer or a boolean, for instance, and second, they are functional tags. So because you could have a boolean could be a light switch, and so then it would be the functional tag light switch, and it would also be the tag, okay, it's a boolean, because the software needs to know it's a boolean that it's interacting with. We can also do nice validation of the data then, because if it's defined as boolean, we can check if there was actually a boolean put in, because corrupt data is, of course, the death of such a system, because then the software will go down. And we have to do it for every object exactly for this multi-inheritance I was talking about. Because when you want to discover something, you have to have the semantic description of the smallest pieces, because then you're most versatile for discovering something in there. But it sounds much worse from the developer perspective than it is, because with one of my bachelor students I was working on validation first, and so now I'm working a little bit with her on also having some assisted Eclipse plugin, where you then have some context-sensitive proposals, like this assistant in Word some years ago that was saying, it seems you want to write a letter. So it could say, okay, it seems you want to write an adapter for a light bulb. So I already have some models, so I can provide them to you. So here's the code, and look if you want to reuse them or not, which is again then fostering this convergence thing. And having this inheritance is very powerful, because it means you don't have to take care if it's a inheritance tree of 20 nodes that you use, but you just look at, okay, what is someone else using? Okay, I can just reuse that, and then you get all the tagging that was done before automatically. So it's manageable like that.
But that is the ontologies you're talking about.
That's the ontology.
But is that the same as the digital twins?
Yes.
Or is that,
It's the same. So the digital twin is actually the ontology, and when we want to go deeper into the ontology, so ontologies, if you ever saw ontologies in computers, so typically something like the web ontology language is used, and there you have triples. So you have a subject, predicate, object. So you have so I'm the subject, am located in is the predicate, and then I could tell the room number, and this would be the object. And so you have these triples. And in our ontology, we only have the triple, we only have two predicates, namely we have is of type and is contained in. So we have this containment, and we have the type relationship. The interesting thing is, when you think this further, what do you want to do in the IoT space? In the end, you just want to access data. And so the only thing you need is you need a unique identifier for each data in there. And so for that, we simply use an ID for the entire space, then we use a node ID, a service ID, and then you can use whatever subaddress, because then your identifier is already unique, and then you can have the same thing on each node. So what did I want to say? Yeah, ontology. So what you can do there is, you can not only do the type-based lookup, but you can introduce additional directory services that are, for instance, handling the location context. And then what are they doing? They are then implementing, for instance, located in or belonging to, and then they have to implement their own lookup mechanism, and then it's working a little bit like the DNS. So you're querying those. This is again transparently possible through the system, because they're all automatically integrated into this search tree. And then you can do the lookup here, and then you get the response, and then you can access the data. And this is quite nice, because it means that dynamically at runtime you can plug in new predicates into the ontology, again in the modular way. Drawback, the resilience goes down if you have just one directory for that, because for the type search we have full replication between all nodes. That means if one goes down, you can still look it up locally. And more important, as this type lookup is very frequent, it's going fast. and deterministic because you don't have to flood the network and you don't know who will answer, for instance. And so this modular concept is there quite powerful also regarding this ontology. And you can also, this is also one work I was just doing with a student, you can also use this as security contexts, because the access scheme that I was talking about is very coarse granular. It's just a binary access scheme. And of course, you typically want to say something like, okay, this service can access the camera, but not the one in my bathroom, wherever you have a camera in the bathroom. But you would want to say that, for instance, and then you can exactly use these contexts by saying, camera in general is okay, but only if not located in bathroom. And then the lookup could be implemented by these KAs again, and they would have to contact with the lookup service and then check if it's true or not, and only then give you access. But this introduces then significant additional latency because this is then one round trip for this service access.
But you bring your cell phone into the bathroom and then you have the camera there.
That's right, but then you can have location detection and say like, it changed the location. Ideally, this would be reflected in the digital world, and then the access rule would work again. Yeah, but yeah, indeed. So exactly, these are the problems that you have there, and these are the problems we have to think about when we design such systems. Because I said at the beginning, so you cannot retrofit security. It's not possible. If someone can access it, someone will access it if it's possible, and therefore we have to think of it from the beginning. And this is also why I want to stress this point so much, because we are now at the point where there is still no operating system for the IoT. But if someone is then successful and this security is missing, then it's totally destroyed because we cannot do anything there. And this is why we have to push that this is in there. So I have another slide that I didn't have there, which I gave for this keynote that I was giving there, where I show the A-bomb. So it was developed, and then I think it was Oppenheimer who said, or at least the people there, was like, okay, yeah, we just delivered a technology, so we don't have to do anything with the use. And so it's a little bit into that direction, because when you think about having an operating system where you can control your spaces, how much power you unleash with having such a thing. And therefore it's really important to also consider this ethical and moral responsibility that we have as developers. And this is something that is luckily gaining more and more importance also in Germany, but still it's not so much in the minds of the people. And so this is why I always encourage my students to also think into that direction, because we have a lot of power and we can deliver something very good to the world, but we also have to take care that it's actually okay what we deliver there. You cannot say, okay, it's just a technology, we don't know what they do with it. Yeah.
So very heretical question. I mean,
Yes.
I mean,
Heretical man.
Yes, that's what we do. Yeah. So if you, I mean, to actually spread such a system, you
Yes.
need big companies behind it.
Yes.
Right? I mean, and these, as you said, these companies actually, they sell me the phone,
Yes.
not because they want me to have the phone, but because they want my data. So
Yes.
how do you get Philips or these companies on board when their goal actually is to have your data?
Yes. Good question. And I think you can just do it by having enough people saying, okay, we only want to buy products that are not in plastic bags, and then it might happen.
Yeah,
And so,
I mean, yeah, of course, but I mean, you know how many stupid people you have that on Facebook say, oh, you want to find out who is in love with you, press this button, and then they send all their data
Yeah.
away, right? I mean,
yeah, so it's like
it's nice to trust on the awareness of the
Yes.
users, but unfortunately,
yes. So for your first question, so the other thing is, I think the only power is that really helps there is a market power. So if people are aware of what they buy there, and if they have alternatives and they decide for the alternative, then you can push it through. Okay, and if it's likely or not, from existing systems, I would say that it's unlikely that this will happen at the moment. But still, I mean, I'm luckily in research, so I can tell the people that they should take care that this happens. And if I tell enough people, maybe I also spot the right people at a certain point in time, and then they tell whoever develops the system that this is needed because they're in the position. For the other thing, indeed, yeah, I mean, if you get the dialogue, okay, this software wants to access your camera whenever it's on your phone, what do you read? You read like, okay, do you want the software to run, yes or no? Okay, yes. And then it can access it. And for that part, this is then again interesting because this is where you have to have some mechanisms that are either making you understand what happens there and giving you options, not only binary, okay, I want this app to run or not, okay, then I say yes. Plus, what you can also do, so I showed this thing with the automatic connection between the different spaces. What you can do if you collect the decisions of the people, if they allow it or not, you can even give people who are unsure what they want to do some automatically inferred average of the other people, which will hopefully be better than, so hopefully the majority of people will then have done the right choice, because otherwise you have again the problem.
Well, go to America and do a presidential election.
Yeah, totally. And then maybe what is said in computer science at the moment, the holy grail of everything is machine learning. So maybe it can do something. No, we're just kidding about that. So yeah, you're totally right. So and my approach to do there is transparency. So trying to give the people enough information so that they can deliberately decide what they want to do. And this is missing, and this challenge is huge because you didn't manage to have it for regular computer programs as well. So the Android phone some years ago, there you could not even distinguish between the different access rights. You could just say, okay, this app wants to have the 20 access rights, do you want to install it or not? And you said yes. And so now I guess it's that you can do it like on the iPhone, that you can select at least, okay, it can only use the location service when it's in the app, or it cannot use it at all. Bringing other challenges from the development side, of course, because if I write an app that needs location access and I don't get it, even if I'm running, I cannot do anything. And so there you have to make clear to the people that why is this information needed, what exactly is needed of this information, and then they have to take a decision. And there I see the big problem for this IoT, that you will have much more decisions than for the phone, because on the phone you just have a couple of sensors and that's it. In the IoT you can sense whatever you can imagine, because if there is no device you can easily build one, and someone will bring it on the market. And this is where it then gets complex, because if you get a questionnaire of 400 items, you will not go through it, because otherwise you just say, okay, I don't install it, or I just say everything yes. And this is again where the automatic mechanisms with, okay, maybe someone looked at it, could work, or some automated analysis saying like, okay, services of a certain type. Good example from the smartphone, where there was this weather app or something that was then also accessing your contacts and so on. Okay, it just doesn't make sense. So weather apps don't have to access the contacts normally, and then you can warn the user saying like, okay, of this 400, 350 are, I mean, it's still bad. 395 are not suspicious and 5 are suspicious. Please consider looking at these 5. And this is something where we ideally would get to. Yes, please.
Something completely different.
Yes.
You talked about that you need the ability to log certain data to access that and not have problems with that. But what if a few different devices try to access the same data and some of them are time critical? Is there some available proof to say, okay, I know that I will at least be able at some point to access that and can consider that? Or is there just the ability for some apps to log data and lock everybody else out?
Very, very, very good question. To the best of my knowledge, there's no solution. I think it's even an NP-hard problem to find a solution for this problem as a whole, but of course it's a limited set of services, so you can then solve it. What we do is the following. So when you lock some data, you lock it only for a certain amount of time, and when you want to keep the lock, you have to actively renew the lock. So this is at least keeping services that went down from blocking this forever, but as you can renew, you have no guarantees until when the lock will be released or not be released. And so this is of course a problem, and so there so in the systems we have running, these problems do not occur, but they are not so we don't have 20 services that want to do something, because in the end the problem that you say occurs very, very often when you think about devices. So think about the controller of this lamp here. When you have 20 applications running that want to access the lamp, you not only have this problem that you do not get access to the lamp, but you also have another problem, namely if 5 services want to put it on and 10 services want to put it off, what do you do? And there you have this typical problem of autonomous or automatic control loops having contradictory things, where you have, for the heating controllers, for instance, typically such hysteresis, where you say, okay, you only switch the state if the majority wants to have it in that direction or in that direction. And so this is some open problem that I don't have a solution for, that I say, okay, someone else might hopefully find something for it. Yeah. But very, very important and very good question, especially when we look at a bigger scale implementations.
Depending on, so as these apps already are tagged and have identifiers, you could try something like at least a priority that every time you want to access something, you give your priority, and if it's locked and the lock is renewed and this one has a smaller priority, then this one loses the lock and the higher priority one gets one. That might be at least at some point the start of the solution.
Yeah, it's exactly the right direction. But when you think about it, then again comes the problem: how many priority classes do you have, and who decides in which priority class you are? And then, but still, you can come to some answers. You can say, for instance, that life critical functionality, like you have fire alarms or something, are always overriding less critical things. But there again, the interesting thing is, the more crowdsourced you do it, the less authority you have. And that means if you want to work against the system, you would always put yourself into the highest priority class. And then you might have short-term benefits for that. Yeah. Yes.
Okay. I think we have to stop now. So
Okay.
thank you again for.
Yeah, thank you very much for the very, very nice.